Good morning, Calc fans. How we doing on this fine Tuesday morning? A little cloudy outside. Weatherman said it's going to get a little bit nicer. Hopefully, it'll get a little bit warmer today. Hope everything's going well in your household. Hope that everything's going well with your family. Please do keep your social distancing. Going to start opening things up in Ohio a little bit. That's a good thing. That's a good thing. Hopefully, we can get back to some sort of normalcy coming up soon here. Today, we're going to talk about the fundamental theorem of calculus. It sounds so important because it's the fundamental theorem of calculus. Okay, and we've already done one of these aspects. There's two parts of the fundamental theorem. We've already done one of them. We're going to do the second one today. But we'll go over the fundamental theorem of calculus. That B being that F, once again, big F, be the indefinite integral for the antiderivative of little f. Okay, so big F is the antiderivative, the indefinite integral for the antiderivative for little f. Then, if I take the integral from b to a, or from a to b of f of x, this is equal to f of b minus f of a. Okay, this is what we've already talked about with respect to our definite integral, but it's also thrown into the fundamental theorem of calculus. It's part one of the fundamental theorem. If I take my antiderivative of my function, I can evaluate my antiderivative b, subtract off the antiderivative evaluation at a. That's part one. And we've already done this. We've called this a definite integral. That's the first aspect of the fundamental theorem of calculus. The second aspect deals with the idea of taking the derivative of the antiderivative. Okay, that the function a of x equal the antiderivative, or then the definite integral from c to x of f of t dt. Is an indefinite integral, or the antiderivative of f, that is a prime of x is equal to f of x. Okay, and this is going to sound confusing to begin with, but as we slow things down a little bit, typically, as we do it in all classes, it will make a little bit more sense for us. Then the derivative with respect to x from c to some derivative or some function g of x of f of t dt. Okay, this is a lot of blah 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 here. We're taking our derivative with respect to x, and we have a function g of x, f of t dt, is equal to the evaluation of our function at our g of x times, once again, now we have to, since we're dealing with derivatives, we have to use our chain rule, times the derivative of g of x. So we're sort of applying our chain rule, and that's what I will refer to as we're applying a chain rule here. Now, the one thing that we had to make sure of is this is a constant. This has to be a constant, okay? Because if not a constant, then we have to deal with another derivative in there. We're not going to be dealing with that. But so to evaluate the derivative of the antiderivative of d of t, okay, this is a derivative with respect to x, but I got d of t here because my function's here, d of t, but my limit of integrations are from constant to a function that deals with g of x. We have to evaluate our function here at g of x and then apply our chain rule, which means I'm going to take times the derivative of my g of x. It's not as hard as it looks. If I have d of x, derivative of x with my integral, and this should be dt, that should be dt. I have a constant here, and that's what I need to make sure of. I have a constant here. I have some function d of x, for d of x. That's one of my my limits of integration. How we calculate this is we just sub this in at the value of t. It's like my upper limit. So we have 1 plus 4x quantity squared all to the 1/2. But then we have to take our chain rule and take the derivative of 4x, which is times the value of 4. Now, if we evaluate this at the lower limit, and why having the constant there, I can put my value of 5 in. So we have 1 plus 5 squared to the 1/2. But then I have to take the derivative of my 5, which is a value of 0, which all just goes away. So if I take a look at this, what we're left with is 4 times 1 plus 16x squared to the 1/2 power. If I wanted to, I could write that as a square root. And this is the second part of the fundamental theorem of calculus. Once again, all we're doing is we're plugging in and then using our chain rule and multiplying by the derivative of our function we're plugging in. And with this being a constant, derivative constant gives 0. The second part goes bye-bye. So this is like f at b minus f at a. But using my chain rule, that f at a goes away. It's like having the value of 0 there, which is nice. So if we take a look at another one, pi is a constant. It is a constant. Once again, this should be dt. We have to plug in our value for x for the t. So we have 2 plus x squared, all squared. But then we have to apply our chain rule, it gives us 2x. Then the derivative, when I plug in the value of pi, I have 2 plus pi squared times the derivative of pi, which is once again 0. So what we're left with is we're left with 2x, and then 2 plus x squared squared. We're going to use this time to also review some other ideas in regards to areas, how we can calculate our areas. We have a function f of x equals x squared minus 1. And I want to calculate my total area between the x-axis and the graph of my function over the interval from -2 to 2. So we are looking at the interval from -2 to 2. I want to find the total area. Now the problem we run into with this total area is, here's my x-axis here. This area is positive, this area is positive, and this area is negative because I'm below the x-axis. So I have to watch what I'm doing here in regards to my area, because if I just do my antiderivative from -2 to 2 of x squared minus 1 dx, what's going to happen is these areas are going to cancel each other out, and we'll have a very, very small area. We need to be able to calculate a total amount of area. So to calculate this total amount of area, I need 3 different integrals. I need the integral from -2 to -1, because this is my value -1 here. This is positive of x squared minus 1 dx. Which is 1/3 x cubed plus minus x from -2 to -1. So we have to evaluate at -1 and then evaluate at -2. Well, if I evaluate at -1, I get 1/3 times -1, which is -1/3, plus 1, minus my evaluation at -2, which would give me -8/3 plus 2. Really have to watch our negatives here. So this gives me 2/3 minus, let's see here, 8/3, which is 2 and 2/3 plus 2, gives me a -2/3 here. We have minus a negative there, that gives me a positive. So my first area comes down to 4/3. So this area here is 4/3. Then I have a second integral from -1 to 1, and let's see what happens here when I go from -1 to 1 of the x squared minus 1 dx. Don't forget your dx in there, please. So I take my antiderivative, it's the same thing. 1/3 x cubed minus x. I need to evaluate from -1 to 1. So if I evaluate at a value of 1, we get 1/3 minus 1. Putting in 1 here and 1 there, minus my evaluation at -1. So we have -1/3 plus 1. This gives me a -2/3. This gives me minus 2/3. This gives me a -4/3. Oops. Which, what we talked about, if I go with this area here and just calculate this area, it's going to give me a negative area. It does. So what we have to do with this is take the absolute value, which gives me another 4/3. And then my last integral is from 1 to 2 of x squared minus x, so minus 1 dx, which is going to give us the same antiderivative, which is 1/3 x cubed minus x, that we have to evaluate from 1 to 2. So we evaluate at 1, we get 8/3 minus 2, minus our valuation at 1, which is 1/3 minus 1. Oops. This gives me a value of 2/3. This gives me minus a -2/3, which gives me another 4/3. So what we have is we have 3 different areas. 2 of them are positive, 1 is negative. What we have to do to get our total area is we have to take the absolute value of this negative to give us a positive. So our total area is 4/3 plus 4/3 plus 4/3. That gives me 2, 4, 8, 12 over 3, which will give me 4 squares. But what I wanted to make sure we knew is when we have negative area, we need to take the absolute value. We just can't take from -2 to 2 and evaluate. If I did that, I would get a value of just 4/3, which is incorrect. Because if I did that, I would get 4/3 plus a -4/3 plus 4/3. These would cancel, it just gives me 4/3. Another idea we have to take a look at is the absolute value. The absolute value. How do I eliminate an absolute value to take my antiderivative? Going back to our definition of a absolute value. Absolute value of x is equal to x when x is greater than or equal to 0. It is equal to -x when x is less than the value of 0. That was our fundamental definition of what we have with respect to the absolute values. Well, what we have is we have x minus 2 here. So if I sub in absolute value of x minus 2, this is going to equal x minus 2 when x minus 2 is greater than or equal to 0. Or when x is greater than or equal to 2. Just adding 2 to both sides. This will equal the negative of x minus 2 when x minus 2 is less than the value of 0. So this is when x is less than the value of 2. What that allows us to be able to do is this allows us to be able to simplify this absolute or expand out our absolute value integral. Because I go from 0 to 5, and during that 0 to 5, sometimes I'm going to be positive and sometimes I'm going to be negative. Because at the value of 2, I separate. So we can break this integral down into from 0 to 2. From the value from 0 to 2, this is when we're less than the value of 2. So this absolute value of x is equal to the negative of x minus 2 dx. Plus the integral from 2 to 5. From 2 to 5, we're dealing with this up here. This absolute value of x minus 2 is just equal to x minus 2 dx. So we have two different integrals that we have to deal with here, because we have to worry about when we're positive and when we're negative. So we have the antiderivatives from 0 to 2 of negative x plus 2 dx, plus the antiderivative 2 to 5 of x minus 2 dx. Taking our antiderivatives, we have 1/2 x squared plus 2x that we have to evaluate from 0 to 2. Sorry, we lost a negative there. Negative 1/2 x squared plus 2x. Plus the antiderivative of x minus 2, which is 1/2 x squared minus 2x that I have to evaluate from 2 to 5. So we have two different integrals or antiderivatives that we have to evaluate here. One from 0 to 2 and one from 2 to 5. So if I evaluate at 2, we have 1/2 times 4, which was, or negative 1/2 times 4, which is negative 2 plus 4 minus my evaluation at 0. If we go to the second one here, we have to evaluate at 5, which is 25 2s minus 10. And then subtract off the evaluation at the value of 2. So evaluation of 2 is 4 times 1/2 is 2 minus 4. So this gives me a value of 2. This gives me a value of, let's see, 25 halves, that's 12.5. So it gives me 2.5 here. Then I have minus, this gives me negative 2. So we have minus a negative 2. So we have 2 plus 2 halves plus a value of 2. This gives me 6.5 squares. So that's dealing with the absolute values. That takes a little bit of practice to be able to get through them, because this here, I found this is the easiest way. This here is the easiest way to be able to simplify and break this out, because what we're going to get is we're going to get a division value. And if that division value happens in my interval, I can separate them. If I'm all positive or all negative, I don't have to worry about separating. But if I have that division value, which is at the value of 2, okay, then I'm going to have to separate it into two different values there. Okay. fundamental theorem, some extra practice with regards to areas, things to look out, watch out for with areas, and also the absolute values here. These are all different types of integrations that we have to worry about and things we have to watch out for in regards to the limits of integration and taking my definite integrals and working with the integrals at that point. I also posted a worksheet for you. The worksheet has some extra problems in regards to the fundamental theorem problems and also some area problems that you can work on. Are provided solutions also in regards to that. I'm not sure if I go through one more. I might go through one more section, then we'll have another quiz over this material. Okay, so continue to work on this and continue to try to keep up with the material that we're dealing with here. We're getting close to the end. We have limits, or we have area in between two graphs. We have integration by substitution that we have to worry about also. We only have 2 or 3 more sections to go through here. So once again, my goal is to hopefully get to us reviewing for the final that second week of May, and we can get the final at the end of the second week of May, or beginning of the third week of May. So that's my hope in regards to completion of this class, but you need to please do keep up with the material that we have. If you have any questions, feel free to contact me at any time. I'll try to help you out as best as possible. If you have questions about the homework, I'll feature them the next day on my notes here, on my videos. Other than that, I have nothing else for you. I miss you guys. I wish you were in class here. But, you know, it's what our reality is at this point. So things are starting to look a little bit better for Ohio, which is good. Let's just keep it going in the positive direction. Keep your social distancing out there. Do the recommendations that they're asking for. Other than that, adios. I'm out here. See y'all.